Hey everyone, it's Mr. Who here, back with another lesson. Recently, we've been talking about functions, observing them in the plane, talking about parent functions, domain, range, and now we're finally going to start analyzing particular kinds of those functions. So we're going to work our way up from lower kind of powers, quadratic, up to polynomial, and then rational. But before we can get to any of that, we do need to return to something you guys might remember from Algebra 2 or Algebra 1 even, factoring. So we're going to talk about four different methods today. Hopefully these are not completely new. You've seen them before, but definitely take a look at them if you need to jostle your memory a little bit. So let's go ahead and get started. So first of all, we got to talk about the very common and very helpful GCF, otherwise known as greatest common factor method. Okay. This is a very simple method. It doesn't really require you to look for any patterns in the problem that's given to you, um, but it can be definitely useful to think about as like a first step, okay? As a first step when you're factoring, all right? So let's go ahead and start something simple here. Okay, so let's go ahead and give you an example here. So if I ask you to completely factor this example problem, 6x plus 3y. Okay, very simple polynomial here. Um, and I'll ask you a factor. You might say, well, I can see that this has 6 and this has 3 in front. I see they have a common factor of 3. So when you factor it, you pull out the 3, right? And what I'm left with is what's multiplied by the 3 to get the 6x. That would be 2x, of course. And what's multiplied by the 3 to get the 3y, that would, of course, be your y. Okay? So that would be my completely factored. So when you take out greatest common factor, you're basically dividing your pieces by the common factor you are looking for. So let me give you a second example just so we can kind of see it in action with variables perhaps. You will have to see those as well. So we do 2x cubed plus 6x squared minus 18. Let's go with that one. 18x. Let's go with that. Sorry. Okay. So in this case, not only do I have numbers in front of all my x's, okay, I see that each of these numbers is even, so I could take out the 2 definitely. But each of these numbers also has an x, okay? So I can also take out this x part. And what I'm left with is, remember, you kind of divide each piece by what you're taking out. So if I divide 2x cubed by 2x, I should be left with x squared. If I divide 6x squared by 2x, well, 6 divided by 2 is 3. X squared divided by x is 1x, 3x. And finally, minus 18x divided by 2x should leave me with minus 9. Okay, so that's the greatest common factor method in a nutshell. Okay, you might have to, rely on some factor trees if you want to find the greatest common factor efficiently, or you can, use some sort of technology to help you find the greatest common factor if it's a number anyway. But for variables, you just got to look if every term has the variable in it, you can take it out. All right, so let's go ahead and talk about the next type. All right. Okay, so the next common type of factoring method we can see is called a difference of squares. Let me actually go in here. See it? Difference of squares. Okay. Now, when we talk about squares, I'm not talking about the geometric shaped square. I'm talking about a perfect square made by multiplying a number by itself. Okay, so let's go ahead and come up with a couple of examples here. Remember, difference means subtraction, so I'll show you a couple of examples and also non-examples to make sure you don't fall for the common mistakes that some people usually do in this field as they're learning the new stuff. So first of all, let's go with something easy. Let's do x squared minus 9. How about that? Okay, x squared minus 9. All right. So if you see these two numbers type of like before in this pattern, it should be ringing in your brain, sending signals all over the place. Okay. You've got a squared minus a squared, okay? But what am I getting, what am I squaring to get those numbers? Okay, that's the important part to think about. X squared is obviously, well, x squared. So this is just x, right? Quantity squared. But what is 9? Okay, 9 is actually another way to say 3 squared. So if you kind of already know how this works and you are pretty confident in your ability to recognize perfect square numbers, you may not need this step. Yeah, I'm writing it out so you guys have the complete thought, the complete view. So I can see that it's obviously two numbers and their squares, okay, being subtracted. So the pattern, guys, is to just take the numbers that are being squared, x and 3, and put them side by side, okay, in a plus minus format. Okay, plus the second term minus the second term. So the first term will always be positive no matter what. You will never have to do anything with that. It's just the second term, you have to flip the sign in the first, and then you got the negative still there as well. If you are trying to do some factoring and you want to like square square something up, okay, which we're not going to talk about now. We're talking about factoring, but we'll soon get to a point we might have to watch out and we might have to remember some foiling. Okay, so that's an easy example. Let's go ahead and do a little bit of a harder one. Okay, something like 49 x to the fourth minus 25 y squared. Let's go with something like that. Okay. So this one obviously doesn't have just numbers, again, like that first example we did in greatest common factor, but it's got two different kinds of variables. So you can't take out the greatest common factor. There's nothing to take out there, right? So when we look at this guy, we have to think about what number can I multiply by itself to get 49x to the fourth. Okay. Well, some of you may recognize 49 is 7 squared, so that is going to start us off. And then you might think, well, what is x to the fourth a square of? Well, remember, we have these things called exponent rules where if you multiply exponented variables together, you can actually add the exponents together. So 2 plus 2 is what I'm thinking of here. Okay. If you take x squared times itself, you have x to the second times x to the second, and 2 plus 2 is 4. So that all works out here. So my first term, oops, not that. So my first term is 7x squared squared, okay, all in parentheses, so remember that part. Okay, and then this 25 square, the square to get to 25 is 5, okay, and then of course y times itself is going to give you the y squared. So here's my breakdown for this problem. I have 7x squared in the front slot and 5y in the second slot. Okay, you can think of those as my a and my b if you were thinking about a formula. Okay. So when I fit it into the form, I should just copy down those numbers. Okay. Remember to group them up in pairs, and then one of them is plus, and the other one is minus. And it's that simple. So that's difference of squares in a nutshell. This method is pretty common, very useful, and I would say it's very easy to recognize. So the more problems you do in factoring, the better you'll get at recognizing them. But this is one of the easiest to recognize, and so you should be able to get it under wraps pretty quickly. Right? Let's go ahead and move on to the third of our four factoring methods. It's just a sec here. Okay, so welcome back. Here's our third method. Our third method is going to be called the ACB tree. Okay, and you may remember this from when we taught it in earlier courses, but this is when we're dealing with things like trinomials. Okay, trinomials. So let's go ahead and make a couple of examples here. These are a little harder to spot, but this is kind of what I'm talking about. So let's go ahead and get a simple trinomial here, a quadratic trinomial, something that doesn't break our brains apart. Let's go ahead and do x squared plus 7x plus 12. Okay, very simple, kind of non-assuming quadratic polynomial, trinomial. Okay, and well, if you're good at the foiling part and undoing the foiling part, you may not need the ACB tree. But what we mean by ACB tree is if you remember the quadratic general form, it has like an ax squared plus bx plus c baked into it. Okay, and so we need to take a look at our coefficients to make ourselves an ACB tree. We have 1 in the front because it's not there, right? So you do have to understand that there is 1. So our A is 1 in this sense. Okay. Our B should be 7 and our C should be 12. Okay. So ACB, So that means what I want is I want A times C, okay? That's going to be 12, right? 1 times 12. And then I want them to add up, or sorry, hang on. I got a little bit ahead of myself, slightly a bit of myself, but you actually want two numbers. You're looking for two numbers, okay, that add up to the B part. So here's 7. So what two numbers multiply into 12 and add up to 7? Okay, you might think, well, I know my factors of 12. They're 1 and 12. That doesn't work because 1 plus 12 doesn't equal 7. I got 2 and 6. That doesn't work. Those add up to 8. But 3 and 4, those definitely work. Okay, they add up to 7. Perfectly fine. So now that you've gotten those two, okay, numbers out, we can split the middle term. Okay, so when we split the middle term, you will now no longer have a trinomial, but you will have a quadrinomial, if you want to call it that. Okay, so it should turn into something like this once you do the ACB tree. Okay, and then we apply a method known as grouping. So grouping can also be used in general if you see 4 terms. That is the same as grouping. But for those of you who are new to this kind of stuff, we kind of group 2 terms together, and then when we factor, we find a common thing to pull out, and we just kind of make it all nice and tidy at the end by turning it into 2 binomials. So let's go ahead and break us down into the first couple of groups. Let me use a different color to indicate what groups I'm talking about. So here's group number 1, and here's group number 2. Okay, so this is going to exercise a bit of that GCF method as well. So when we factor these 2 groups by themselves, okay, it should be fairly obvious what you need to pull out. So in this first group, I only have x squared and 3x. What I can pull out is that x, of course, and what I'm left with is the x plus 3. Okay, seems good enough. The next group is 4x plus 12. I only got numbers in one of the terms, so I know I can't pull out any x's. What I can pull out is the 4. Okay, but what is left? X plus 3. So in this step, you definitely need to look for this kind of idea of your groups, okay, becoming the same in the end. So that is definitely useful to know. I highlighted them for you so you know that when you do this kind of method, you do this grouping method after an ACB tree, the things in the parentheses need to be matching. Finally, the final step to make it all nice and neat looking is to just say, well, I have 2 groups, okay, being multiplied by some number of things, okay, and so I can split them apart and go like that. All right. So that is ACB tree in a nutshell. I feel like this one you will definitely need to get a little more practice. You'll need to practice this a lot more in order to get better at it. Okay. But it is there for there. But there for there. It is there for now in this simpler form. Okay. But do know that there are plenty of harder ones that involve a different A than 1. Okay. And different B's and C's as well. So if you want any of those examples, you can definitely try going to Delta Math and figuring that out. But for the purposes of this video, I don't want to kind of go through that. And don't worry, at the end of this all, we'll have a little bit of a list to tell you what the steps are. All right, let's move on to the final of the 4 factoring methods we got today. All right, and so the final method we're going to talk about today is something called difference of cubes, as well as something called a sum of cubes. Now, if you've seen this one before, you should know that this is a very similar to the difference of square kind, but instead of looking for a squared number, you're looking for a cubed number, a cubed term. So here's one such example, okay? It's going to be very simple, x cubed minus 1. Okay, so this is obviously a difference of 2 terms, right? And x cubed is obviously going to be x cubed, right? So, and 1 times itself 3 times is definitely just 1 cubed. Okay, so you can definitely split it apart like that. So that recognition part is very important. If you can recognize it, you should be able to get this factoring method done just like the difference of squares one. However, a little bit harder than the difference of squares one because this has a little bit more formula attached to it. So when I see this, you're going to have two groups just like the difference of squares, okay? And they involve the terms, right? However, there is going to be a third term in the second pair, or the second parentheses set. And I'll get to that in a sec. But we see the minus here, so I'm going to put minus here. Okay, so in the little group, the two-piece group, you got to put the same sign as what you see up here. And then in the second group, if you have minus, it's going to be plus and plus, okay? And that middle term is just the two terms multiplied by each other. In this case, it would be x times 1 or just x. And then these would be squared. Okay, those two things on the ends. I'll go ahead and put an x times 1 so you know I'm not losing it. Okay. All right, so that is the basic formula. I'll write it out as well at the end here. So that's a difference of cubes. How about a sum of cubes? So, you know, sum of squares, that's not really a thing, so I wouldn't worry about looking for the sum of squares, but a sum of cubes we can definitely do. So let's go ahead and give you an example of that. I'm going to use y cubed, 8y cubed, plus, let's use 27. How's that? 8y cubed plus 27. Now, this is where your kind of math sense starts to have to develop here. If you know what the cube root of 8 is, okay, what number you multiplied by itself 3 times to get 8, that is actually 2. Okay? And of course, y times itself 3 times is y cubed. So our first term, cubed, when you cube root it, is 2y. All right, and our second one, 27, is the result of cubing 3. And remember, this is a plus. So here's my two pieces. Okay, I need to put them into my little formula. So the first little pair will have those two. Remember, it's plus up here, so just copy that down in the first pair. Then I have something squared, the left one squared, so that'd be 2y quantity squared. Okay. Then here's where it gets a little different if you're just talking about sum. In sum of cubes, you have to alternate minus, okay, and in there, and then plus at the end. But we'll get to that in a second. So this middle term will be 2y times 3. Okay. And then I'm running a little bit out of space, but you have 3 squared. Parentheses. It's a little cut off, but I think you guys get the point. Okay. So let's go ahead and simplify a little bit. 2y plus 3 in the first pair. Then 2y squared. Remember, you got to apply the 2 to both of them. So that's 4y squared. Then 2y and 3, they multiply very nicely to 6y. And 3 squared is just 9. Okay. And that's it. That's the factorization. Okay. There is nothing else you need to do for this kind of factorization, even though it looks like it can still be factored. This thing in the right is a trinomial, so you might want to try something like an ACB tree on it. But fact of the matter is, in difference in sum of cubes, those things just don't factor anymore. They're completely factored. Okay, so hopefully you've seen those. Let me put the formulas up on the final slide, the final kind of like summary slide of all my factoring methods, so you guys can go look at that. And I'll give you a sec to write that down before I end off this lesson. Okay, so I'll be back in just a sec. Let me clear the board. All right, scholars, you've made it to the last little slide of our presentation today. Um, there are the 4 methods I've placed on the board, okay, with the little sections to mark them off. But I am going to kind of talk about how you can spot these, how you can spot which ones to use. So the GCF method, this is a universal method, okay, so it can work on anything. Okay, it could work on anything. Now, if the greatest common factor is, of course, 1, then you can't really factor anything out of it. Okay, that's what we consider completely factored by GCF. You won't be able to take any other factors out. However, if you can take out any factors at all, you will have to do so if you want to consider it completely factored. I'm sure Delta Math will knock you if you don't completely factor certain parts. Okay. But GCF, you remember, is you take out a greatest common factor, you divide your polynomial or whatever your problem is by the thing you're taking out. But it still stays out there. You're not getting rid of it, but to get the little inside, what's left, You do have to do that. Difference of squares, okay? Now, when we did those examples, I basically used a couple examples that form this general form, a squared minus b squared. Okay. If you can recognize that form, then you can apply the formula, which is to just change them into a plus b, a minus b, and those will be multiplied together. So it's as simple as that. There is no such thing as a sum of squares. Please do not do anything with a squared plus b squared. Those don't exist. Okay. All right. Difference or sum of cubes. So I'm going to split this one in the middle here. Okay. So if we have a difference of cubes, okay, then you'll be looking at something like a cubed minus b cubed form, right? And your written answer should look something like, oops, undo that, a minus b times a squared plus ab minus b, or plus, sorry, b squared. That's the form you should fit with the form. And next, finally, is the sum. It would be a cubed plus b cubed. And similar to the above, you're going to be looking at an a plus b times an a squared minus ab plus b squared. Very similar, but watch the signs on this one. Okay? Watch the signs. Now, the reason I left this third method we talked about, the grouping and ACB tree, for last is because it's kind of special. So the ACB tree we usually use for trinomials, okay? It could be quadratic, could be quartic, okay? Anything where the degrees on the highest is on the left and the lowest is on the right, okay? That standard form, we call that. And grouping is for four-term polynomials. So if you ever see a four-term polynomials, you can try grouping on it, okay? Remember, the general is a times c equals some sort of number, okay? And then you want to get the factors that would add up to c, or not c, b, ACB, not ACC, ACB. Okay, so sorry about that little chicken scrawl, but you want to find two factors, okay? I use a different marker for this, so you guys know what I'm talking about. Two factors of number. And then I'll change back to black for that one. Okay. So that is how you do the ACB tree. That's that part. Now remember, the grouping part would be to group and then GCF. So split your terms up, apply GCF. So if you're a whiz at GCF, this grouping thing should also be pretty simple and straightforward for you guys to take advantage of. All right. And that's pretty much it. So I really think this kind of stuff for mastering this, you just have to do a lot of different exercises, okay? So when you do the delta math on this one, please come up with any questions so we can help you on that one. And remember, if it's a multi-step factoring problem, okay, you might have to use more than one of these per problem. Okay? So you might have to do a combination of difference of squares and GCF. You might have to do, oh, there's an ACB tree with a difference of squares. Okay, stuff like that. But keep factoring until you can no longer factor. And we can definitely go over that in class if you guys have questions. Okay. Thanks for tuning in to another exciting episode of Mr. Who's Given Some Math Lessons. All right. And I hope you guys are having a great day. See you all later.